Hi students, welcome to our last week of course content for the semester. This is week 14. We will be covering binary logistic regression. Before I get started on the handout overview, I want to go ahead and just review the course schedule. Okay, this is where we're at here. We will be covering binary logistic this week. What you have coming up is Pop Quiz 9 on Friday, 4/24. And on the 27th, Monday, you have your final assignment due. Then you have your last pop quiz, Friday, May 1st. Okay, that is the day that I will be releasing your final examination on Blackboard. You will have a week to complete the final examination. I will be available to chat over the phone these days here, Monday and Wednesday, if you need anything or have any questions. Your final exam is then due Friday the 7th by 9 p.m. Okay, so work hard, study hard, and let me know if you have any questions or concerns. Okay, let's go ahead and start our lesson. Binary logistic regression. This is a type of regression similar to the linear regression models that we discussed last week. However, binary logistic regression is specifically designed when you are estimating an outcome variable that is dichotomous or binary. Okay. So again, logistic regression is an extension of standard linear regression. However, it's used in instances when our dependent variable is dichotomous or binary, because remember, when we are using linear regression, the outcome variable must be continuous. So then what do you do when your outcome variable is not continuous? What do you do when it's binary? Well, you use binary logistic regression. Okay. We cannot just stick a binary variable into linear regression and get valid results. Okay. This is why scientists have designed logistic regression. So logistic regression in particular looks at the relationship between independent variables, multiple independent variables. They can be any type of independent variable, categorical or continuous, and a binary dependent variable. An example of this is sex, which has two categories, male and female, or if you have any type of variable that uses a yes or no response, you can also use binary logistic for that. If you have a score, for example, that is split up into a high or low category, binary logistic regression can work. Okay. So let's quickly go over just some of the basic requirements for logistic regression. Of course, as I mentioned, your outcome variable has to be binary or dichotomous, coded as 1 or 0. Okay. When it comes to your predictors or your independent variables, you must use 2 or more. Okay, so you can't just use one like simple linear regression. If you want to use binary logistic, you have to have 2 or more independent variables. Okay, again, these independent variables can be continuous or categorical. Now we're just going to quickly go over why it is that we cannot just use regular linear regression. Okay. In linear regression, when we are estimating a continuous outcome, this outcome variable is interval level, and it is what we call unbounded. This means that it can take any numerical value. It can be negative, it can be positive, it can be negative infinity or positive infinity. There is no bounds on what the estimate can be. Okay, but this is not the case for binary measures. Okay, well, the essence of binary variables are that they indicate 1 or 0, yes or no, affirmative, negative. Okay, they are bounded by this dichotomy. Okay, this means that its estimates need to fall within that range, 1 or 0. Okay, estimates cannot be less than 0 or greater than 1. Okay, which is what linear regression produces. Okay, if we were to use binary variables in linear regression as an outcome, it's going to treat them as unbounded, and it's going to produce estimates that are outside of those bounds. Okay, and that is inappropriate, and it will not give you efficient estimates. Okay, now binary logistic regression is tricky in that the interpretation of its results are different than the interpretation of results in standard linear regression. Okay, this is because the nature of binary variables means that it is interpreted in a specific way. Okay, if we were to derive the average or the mean of a binary variable, it equals to a value that is interpreted as a probability. And I'm not sure if you guys have a background in probability, but it equals to the proportion of cases that are coded affirmatively as 1, okay, which is representative of the overall probability of whatever the variable is measuring. Okay, so let's say we have an outcome variable that is measuring success, and success can be yes, I was successful, coded as 1, or no, I was not successful, coded as 0. Okay, if that value produced an average of, let's say, 0.8, okay, this means that our probability of success equals to 0.8. Okay, our probability of success is equal to 0.8, which is the mean of a binary variable coefficient. Okay, if we want to calculate the probability, okay, of the failure of success also, right? We know the probability of succeeding is the mean. What if we want to know the probability of failure? To do that, we would subtract 0.8, which is the probability of success, from a total of 1. Okay, this is going to give us a value of 0.2. So 0.2 would be the probability of failure. Okay, now this is all just kind of confusing. Probabilities in and of themselves are extremely confusing. They're very difficult to interpret because they are not very intuitive. Okay, now we do use a much more intuitive method to interpret logistic regression results. Okay, the intuitive coefficient that we use is called an odds ratio. Okay, when you are using SPSS, that odds ratio is denoted as the I can't say that word, exponented B, okay, the B coefficient. So if we want to derive this odds ratio, okay, we need to calculate the odds of success. And the way to do that is we take a ratio of the probability of success over the probability of failure. And if we look back at these coefficients up here, we know that that is 0.8 divided by 0.2. This results in an odds ratio for success that is 4 to 1. Okay, now I'm going to make this simple for y'all. Okay, in SPSS, we don't have to manually calculate the odds ratio. It will just spit out the odds ratio coefficient. And the way to interpret those odds ratios is when the odds ratio is over 1, okay, we would say that the odds of success increases as the predictor increases, okay? On the contrary, if the odds ratio is less than 1, we would say that the odds of success decreases as the predictor increases, okay? So this is going to make a lot more sense once we get hands-on with SPSS. So I'm going to conclude this handout lecture. Go ahead and tune into the next video where we will open up SPSS and tackle binary logistic regression.